Number 2, we've got a long straight wire. It is carrying a current into the page, and we want the direction of the magnetic field at point P due to the current. So when we have a current into the page, we use the grip rule, we curl our fingers, and we can see that the magnetic field is curling this way, which means at point P, it's going to be pointing downward. Part B says use Ampere's law to develop an expression for the magnitude of the magnetic field at point P. Ampere's law we haven't covered yet, so I'm just going to give you the answer to this one. You're going to do a lot of practice with Ampere's law with the next problems for tomorrow's or next class's homework. So for now, just use this equation for your answer to B. It's going to pop up again when you do the equations down here for C and D. So don't worry about how it's derived. In fact, it's one of the equations that you were given in the Biot-Savart unit for current carrying wire, but we'll be able to show how it's derived using Ampere's law as well by next class. Okay, so this next one is what is the magnetic field at point 0, midway between the two current carrying wires. So both of the wires are going to be having a current into the page as the magnetic field for the left wire, as the current goes into the page, the magnetic field goes in a clockwise direction, which means that at 0, it's going to be, at the origin, it's going to be downward. And then here, as it goes into the page, it's going again in a clockwise direction. So as I expand this circle, it's going to go up at the origin. So you're going to see here that the magnetic field is actually, net magnetic field is actually 0 because the current is the same and they're an equal distance away from the origin. So that means the magnetic field is going to be equal and opposite. All right, physics students, so we're going to make another attempt at 2D and E. The angles were messed up, so let's make sure to... All right, physics students, so we're going to make another attempt at D and E. There was an error in the answer key, and in the answer key video, so I want to make sure to give you the correct solution. So in this scenario, we've got a magnetic field into the board for both currents, so we are going to have a clockwise magnetic field for both. It's going to create that same shape, just a bigger magnetic field circle at A, which means it's going to go up and to the right. Same here, it's going to be up and to the left. Now, to avoid kind of drawing too many circles, we can see here that the magnetic field in the y direction is going to equal 0. They have the same current, they have the same distance from A, so they're going to be kind of opposite of each other. So the y components cancel out, but the x components are going to add together. So we're going to get double the magnetic field, and we're going to figure out what component that is. So I'm going to leave this blank. The way we analyze, let me just get rid of this guy. Not getting great results. Okay, so what we want to do is just analyze one magnetic field first. We can double it once we get that component, but this line is our distance. We can call that the square root of r squared plus y squared. And it has a directional vector of value 1, r hat. This r hat, because it creates a magnetic field, the magnetic field B is going to be perpendicular to r hat because it's tangent to that magnetic field circle. And then we have to analyze how we can get this component here. So first off, our theta is always from r hat to the axis that it is kind of branching off of. And we can see that we've got a 90-degree angle here. So in order for all the angles to sum up to 180, this angle must be 90 minus theta. I've also got 90 degrees here and a straight line of 180 degrees right here. Therefore, we can see that in order for this straight line to be 180 and this being 90, we would want this guy to be theta. So I'm going to take the x component using theta of the magnetic field up here at the top. So if this is theta, we're actually taking the opposite over hypotenuse, which is b sine of theta. Sorry, I'm having brain farts today. So opposite over hypotenuse, my bx is 2b sine theta. I'm taking the b from part b of this problem, and then I'm just going to plug in the values. Mu naught I over 2 pi r, which is the square root of r squared plus y squared, times sine theta. For that, I want to go to my triangle, and the sine of this triangle's theta is going to be the same sign as my magnetic field's theta. So it's opposite over hypotenuse. That gives me y over r squared squared plus y squared. The square roots can eliminate each other, same with the 2. And so my b x component is mu naught I y over pi times r squared plus y squared. For part E, let's clean this up a bit. We have a magnetic, a current coming out of the board rather than into the board. So I'm going to have a counterclockwise current here, which means that my current is going to come up and to the left. We can see then that my magnetic field for E in the x direction is going to equal 0, and my magnetic field for y, if I sum it all together, is 2b. This is still theta, but now we want the y component. So this component right here, which is adjacent over hypotenuse, that's cosine theta. So I'm going to do the same thing I did. 2 times mu naught I over 2 pi. R is r squared plus x squared. And then cosine of my triangle is adjacent over hypotenuse. So that's r over square root of r squared plus x squared. And my 2's cancel out. These combine together. My net magnetic field for E is going to be mu naught I r over pi times r squared plus x squared. And this is the y component.